Before the 18th century, the subject of electricity and magnetism were thought to be different. It was in 1820 that Hans Christian Ørsted, a Danish scientist, discovered the connection between these phenomena. During an experimental demonstration on electricity, he observed a noticeable deflection in the magnetic compass needle placed near a current-carrying conductor. Let us understand the experiment. In the first case, a magnetic compass is placed below a straight conducting wire with the length of the wire in the north-south direction. The magnetic compass is also in the north-south direction when the current is not passing through the wire. If current passes through the conductor in the south-north direction, the magnetic needle deflects towards the west. In the second case, if the direction of the current is reversed and the current is now allowed to pass through the conductor in the north-south direction, then the deflection in the magnetic compass needle placed below the conductor is towards the east. In the third case, the deflection of the magnetic compass needle can also be observed by placing the magnetic compass above the straight current-carrying conductor. If current passes through the conductor in the south to north direction, the magnetic needle is deflected towards the east. In the next case, if the direction of current is reversed and the current is now allowed to pass through the conductor in the north-south direction, then the deflection in the magnetic compass needle placed below the conductor is towards the west. All these situations were observed when the current passing through the conducting wire is large and the magnetic needle is placed sufficiently close to the wire so that the Earth's magnetism may be ignored. It was also observed that when the magnitude of current passing through the conducting wire was increased, the deflection of the magnetic needle placed at a constant distance from the conducting wire increased. When the magnetic compass moves closer to the conducting wire for the same amount of current passing through it, the deflection of the magnetic needle increases. In another demonstration, the magnetic field due to a straight current-carrying conductor could be found by placing a cardboard in a horizontal position and passing the conductor through a hole at its center, such that the length of the wire is perpendicular to the plane of the cardboard. Some iron filings were sprinkled on the cardboard. As soon as the current passes through the conductor, the iron filings orient themselves in concentric circles, with their center coinciding with the center of the conductor. From these observations, Ørsted concluded that current in a conductor produced a magnetic field around it. He also found that the alignment of the magnetic needle is tangential to an imaginary circle with straight current-carrying wire at the center, and the plane of the imaginary circle is perpendicular to the length of the wire. To represent the magnetic field produced by a straight current-carrying conductor, on paper, we adopt the convention for magnetic field emerging out of the plane of the paper, which is denoted by a dot. The magnetic field going into the plane of the paper is denoted by a cross. Now, let us see how a charge at rest produces only an electric field, and a charge in motion produces both an electric field and a magnetic field. We know that like charges repel each other and unlike charges attract each other. This interaction can be seen as a two-step process. First, a charge produces something around it in a space called an electric field, and this electric field exerts a force on any charge except the source charge placed in it. Let a source charge Q be placed at a point in a vacuum. The space around the charge, where it can influence other charges, is called its electric field. As step 2, a small test charge Q is placed at point P in the electric field, at a distance r from the source charge Q. Then the intensity of the electric field at the given point, P, is defined as the force per unit charge. According to Coulomb's inverse square law, the force between the two charges is F is equal to QQR cap divided by 4 pi epsilon naught r square. Let this be equation 1, where r cap is the unit vector along the force vector and epsilon naught is the permittivity of the free space or air. Then the intensity of the electric field at point P is denoted by E is equal to F divided by Q. Let this be equation 2. Substituting equation 2 in 1, we get the intensity of the electric field as E is equal to QR cap divided by 4 pi epsilon naught r square, where r cap is the unit vector along the electric field vector. The electric field has its own existence and is present even if there is no additional charge to experience the force. Thus, the field due to Q exists even in the absence of the additional charge Q. The field can convey energy and momentum and is not established instantaneously. The field takes a finite amount of time to propagate. Thus, if the charge is displaced from its position, then the field at a distance r will change after a time t is equal to r divided by c, where c is the speed of light. But while dealing with electricity and magnetism at this level, we will assume that the field due to a charge at a given point does not change with time at a given place. If there is more than one charge in the space under consideration, the electric field at a particular point is due to more charges. Consider 3 charged spheres with charges Q1, Q2, and Q3 placed at different locations as shown. Then, the fields due to all the charges should add vectorially. This is called the principle of superposition. If E1, E2, and E3 are electric fields due to charges Q1, Q2, and Q3 respectively at point P, the resultant electric field at point P is E is equal to E1 plus E2 plus E3. This is with regard to charged bodies or charges at rest. Let us now learn about charges in motion. If a charge Q is placed near a current-carrying conductor at point P, it does not experience any force because there is no electric field at point P. Since the conducting wire contains an equal number of positive and negative charges, it is electrically neutral and hence does not produce a net electric field. If the charge Q is projected from point P in the direction of the current in the wire, the charge gets deflected towards the wire if the charge is positive, and away from the wire if it is negative. If the charge Q is projected from point P in the opposite direction to the current in the wire, the charge gets deflected away from the wire if the charge is positive. and towards the wire if it is negative. From these observations, it is clear that there must be another field other than the electric field that exerts a force on the charged particle, Q. This new field exerts a force on the charge Q when it is moving. This new field is the magnetic field created by charge Q when it is in motion. Magnetic field is denoted by the letter B. The current in the wire is nothing but charges in motion. Thus, there is a magnetic field due to the current, and this magnetic field interacts with the magnetic field due to the moving charge Q. The interaction between these two magnetic fields causes the charge Q to deviate from its path. Thus, the moving charges produce both an electric field and a magnetic field.